98%. That number appeared on the Finance Bench leaderboard, and the RAG community has not been the same since. For context, most production RAG systems running on top-tier vector databases and the latest LLMs are sitting somewhere between 70 and 85% on this benchmark. Some well-tuned systems push into the low 90s, and then PageIndex and posts 98%. Without a single vector database in its architecture, no embeddings, no cosine similarity search, no Pinecone, no Weaviate, no Chroma. None of it. The moment I saw this result, my first instinct, like any senior engineer, was to look for the catch. Was this benchmark cherry-picked? Is it measuring something trivial? Is this another paper result that collapses the moment you touch real documents? I dug in, and what I found should make every engineer currently building or planning a RAG pipeline stop and reconsider their assumptions. By the end of this video, you will have a clear, evidence-based answer to the question, does PageIndex actually work, and should you replace your current RAG stack with it? But a benchmark result alone proves nothing. The RAG ecosystem is full of systems that look great on paper and fall apart in production. So let's look at what the broader developer community did with this result. Vectify AI's PageIndex repository crossed 23,000 GitHub stars in a matter of weeks. For a library in the RAG tooling space, that is an extraordinary signal. Compare that to the growth curves of established vector database clients. Most took over a year to reach similar traction. The community posts were equally striking. Senior engineers at major tech companies were not just saying interesting. They were writing threads about whether their entire embedding infrastructure investment had been a mistake. That kind of reaction does not happen over incremental improvements. It happens when something fundamentally challenges the architecture that everyone assumed was correct. Now here is what I want you to hold in mind. Explosive GitHub growth and community excitement have burned engineers before. Hype is real. So the question we need to answer is not whether PageIndex is popular, it clearly is. The question is whether the architectural decision behind it is structurally sound. And that question takes us directly into how this system actually works, which we will dissect starting in the next section. Let me be direct about what this video will and will not do. This is Nondex's promotional piece, and it is not a piece either. It is a structured engineering evaluation. By the time the final chapter ends, you will be equipped to make exactly 3 concrete decisions about your own RAG infrastructure. First, should you adopt PageIndex immediately? This applies if you are building document-heavy financial, legal, compliance RAG systems, where accuracy is the primary constraint and your current vector DB pipeline is underperforming. Should you run a controlled pilot? This applies if you have a working RAG pipeline, but you are hitting an accuracy ceiling around 80 to 85%, and you want to, whether the architectural trade-offs of PageIndex justify the migration cost. Third, should you skip it entirely for now? This applies if your use case involves real-time retrieval over massive scale corpora, or if multilingual support beyond English is a hard requirement. Because as we will see, PageIndex has real constraints in those areas. Every decision needs a framework. Every framework needs evidence. Both. Here is the evaluation framework this video uses, because I want you to be able to replicate this analysis on your own data, not just trust my conclusions. We will measure PageIndex across 4 dimensions. Accuracy. Using Finance Bench as the primary benchmark, but also testing against Korean language financial documents. Because most English-only benchmarks are useless if your production data is not English. Cost. Total infrastructure cost compared to a Pinecone-backed equivalent pipeline at identical document volumes. Complexity. How many moving parts, how much operational overhead, and how steep the learning curve is for a team that has never touched this architecture. And finally, production readiness, latency, failure modes, and the scenarios where PageIndex breaks down. I am going to show you the Korean document test results, because that is where the gap between benchmark performance and real-world performance becomes most visible. If a system can maintain near-perfect accuracy on English financial PDFs, but drops to 60% on Korean regulatory documents, that tells you something critical about the architecture's actual mechanism. And understanding that mechanism is exactly what the next chapter is about. Because to understand why PageIndex works, you first need to understand precisely how and why the classic RAG pipeline is broken. Let's start with the part of the RAG pipeline everyone glosses over in tutorials: chunking. When you chunk a document, you are making an irreversible decision about how information is sliced and stored. Fixed-size chunking. 512 tokens sounds clean and efficient, but documents are not written in 512 token units. A financial report has tables where row 3 only makes sense in context of the column header in row 1. It has footnotes that reference clauses on page 12 from page 47. The moment your chunk boundary lands in the middle of a multi-row table, or severs a footnote from its anchor, you have not just lost data. You have created a structurally coherent-looking fragment that will confidently mislead your retrieval system. Recursive chunking tries to respect paragraph breaks, but paragraphs in regulatory filings routinely span multiple pages. The document's semantic architecture, its hierarchy of headings, subclauses, cross-references, is completely invisible to a chunker that only sees raw token counts. And here's what makes this dangerous. The damage is silent. Your pipeline doesn't throw an error. It just quietly returns wrong answers with high confidence. But the chunking problem is only half the story. Wait until you see what happens inside the embedding layer. So the natural question is, can we just tune the chunk size to fix this? The answer is no, and this is the core structural trap of vector RAG. Make your chunks small, say 128 tokens, and each chunk is precise and focused. Great for retrieval granularity. But now a single financial clause that spans 600 tokens is split across 5 chunks. The embedding for each fragment captures only a narrow slice of the concept. When a user queries about that clause, the top K retrieval might pull 3 of those 5 fragments, not necessarily the right 3, and the LLM is now reasoning over an incomplete, non-contiguous picture of the original text. On the other hand, make your chunks large, 2,000 tokens, and now each chunk is semantically dense. But dense embeddings are noisy embeddings. The vector for a 2,000 token chunk is trying to represent too many ideas at once. So it ends up being weakly similar to many queries and strongly similar to almost none. You get false positives, chunks that score well on cosine similarity but contain the target information buried under unrelated content. There is no chunk size that solves both problems simultaneously for complex, heterogeneous documents. This isn't a tuning problem, it's a structural ceiling, and the numbers on Finance Bench prove it. But first, let me show you a concrete failure case. Let me make this concrete with a real-world pattern from financial document analysis. Imagine an annual report where footnote 23 on page 47 states, see revenue recognition breakdown as described in Note 4, Table 2. Note 4 and its table sit on page 12's 35 pages, and dozens of chunk boundaries earlier. A standard chunking pipeline stores footnote 23 in one chunk and Note 4's table in a completely separate chunk, with zero explicit link between them. When a user asks, what is the revenue recognition method applied to software licenses? The query embedding lands near footnote 23's chunk. That chunk gets retrieved. The LLM reads it and encounters a dangling reference to a table it has never seen. It either hallucinates a plausible-sounding answer or says the document is unclear. Both are failures. The cross-reference that would have answered the question correctly exists in the original document. Your chunking strategy destroyed it. This is not an edge case. In Finance Bench, over 40% of questions require cross-referencing information from non-adjacent document sections. Vector RAG's chunking layer structurally cannot handle this class of queries. So before we can talk about the solution, we need to understand why the embedding layer doesn't save you either. Most postmortems on failed RAG systems blame the embedding model. We need a better embedding model. Let's fine-tune on domain data, switch from OpenAI ADA to a finance-specific encoder. This is the wrong diagnosis, and it leads teams to spend months on the wrong fix. Here's the critical distinction you need to internalize. Embedding models measure semantic similarity, how closely 2 pieces of text share surface-level meaning and vocabulary. But financial and technical documents require logical and hierarchical reasoning. Revenue decreased due to Clause 4.2b, as amended in Q3, is logically related to that specific clause, not to every other sentence that mentions revenue decreasing. An embedding model will score it as highly similar to any text about declining revenue, regardless of whether that text contains 4.2b. This is not a model quality problem. It is a fundamental mismatch between what vector similarity computes and what document reasoning requires. Even a perfect embedding model operating on correctly chunked text cannot represent the fact that conclusion B is derived from cross-section boundaries. Vector space has no axis for logical dependency. It only has axes for distributional co-occurrence in training data, and there's a second failure mode that's even more insidious: vector space collapse under domain shift. When you feed a general-purpose embedding model a document dense with specialized terminology, GAAP accounting standards, SEC filing codes, regulatory references, the model maps unfamiliar token sequences into compressed, overlapping regions of the vector space. Semantically distinct concepts end up with high cosine similarity simply because the model has never seen enough domain-specific training data to spread them apart. The result, your retrieval confident, plausible, wrong answers. But how bad does this get in practice? The table in the next scene will make you reconsider every raggy deployment you've ever shipped. This is where theory meets reality, and numbers are brutal. Let me walk you through documented failure patterns on Finance Bench, the standard benchmark for financial document question answering that uses real SEC filings from public companies. Look at the first failure mode, semantic drift. A query asks about Apple's effective tax rate for fiscal year 2022. The top one retrieved chunk is about Apple's deferred tax liability. It mentions tax, fiscal 2022, and effective rate multiple times. Cosine similarity is high, but deferred tax liability and effective tax rate are different financial metrics. The LLM, given only this chunk, computes and returns the wrong number with complete confidence, no hallucination warning. Just a factually incorrect answer that looks authoritative. Second pattern, temporal confusion. A query about Q4 2022 revenue retrieves a chunk discussing Q4 2021 revenue because the language is nearly identical. Same company, same product lines, same reporting format, different year. Vector similarity cannot distinguish temporal specificity. Third, scope mismatch. A query about consolidated group revenue retrieves a chunk about a subsidiary's revenue. Both use identical financial language. Embedding model scores them as equivalent. These aren't hypothetical failure modes. Leading vector RAG systems on Finance Bench score between 44% and 60% accuracy on this benchmark. That means on a real financial QA task, your RAG system gets the wrong answer more than 30% of the time, and you often cannot tell which answers are wrong. So when did we decide this was acceptable? Let's look at how we got here. To understand why vector RAG has hit a ceiling, you need to trace how we got here. Each generation of retrieval technology solved the problems of the previous era, and in doing so, introduced the blind spots of the next. It started with BM25 in the 1990s, pure keyword matching with term frequency weighting. Fast, interpretable, still unbeatable for exact match queries. But it fails completely when the user's vocabulary doesn't match the document's vocabulary. That gap gave birth to dense retrieval around 2020, with models like DPR, dense passage retrieval from Facebook AI. Now you could match revenue decline to sales dropped, because both map to nearby vectors. This was a genuine leap. Naive RAG followed immediately. Take a dense retriever, attach an LLM, ship it. Developers were building production systems in days. The benchmark scores looked promising on simple QA tasks. But as documents got more complex, longer, more structured, more cross-referential, the failure modes we just discussed started showing up in production. The community's response was advanced RAG, add re-ranking, add query rewriting, add hybrid search combining BM25 and dense vectors, add sentence window retrieval, add parent document retrieval. Each edition patched a specific failure mode. But here's what the benchmark started revealing around 2023 and into 2024. All of these improvements are asymptotically approaching a ceiling. You can tune the retrieval pipeline indefinitely, but if the fundamental representation, chunks in a flat vector space, is wrong for the document type, no amount of re-ranking saves you. The ceiling is architectural, not algorithmic, and the Finance Bench numbers make that ceiling painfully visible. Let's put hard numbers on that ceiling. Finance Bench is the most rigorous public benchmark for financial document QA. 150 questions drawn from real SEC CKA and 10Q filings from major public companies. Questions require multi-step reasoning, cross-section referencing, and precise numerical extraction. This is exactly the workload that production RAG systems in finance, legal, and enterprise settings actually face. Here's what the benchmark shows for leading vector RAG implementations as of 2024. A well-tuned, naive RAG baseline with GPT-4 retrieval sits around 45 to 52% accuracy. Add re-ranking with a cross-encoder, you get to roughly 60 to 63%. Add hybrid BM25 plus dense search, fine-tuned retriever, sentence window context. The best published vector RAG configurations on Finance Bench reach approximately 68 to 70%. That number has not moved significantly in over a year of active research and engineering effort from multiple teams. Meanwhile, PageIndex reports 98% accuracy on a comparable benchmark set. That is not a 10-point improvement. That is new soda by a few points. That is a different category of result. The kind of gap that tells you the underlying approach has fundamentally changed. So the question is, what exactly changed? Because that 30-point gap between 68% and 98% doesn't come from a better embedding model or a smarter re-ranker. It comes from abandoning the flat chunk embed paradigm entirely. And that is exactly what we'll unpack in the next chapter. How PageIndex builds a semantic tree instead of a vector index, and why that single architectural decision makes all the difference. So the previous chapter exposed the structural failure of classic RAG, flat chunks that destroy context. Now let's get at exactly how PageIndex solves this at the architectural level. The core idea is deceptively simple. Stop treating documents as bags of text, and start treating them as what they actually are, hierarchical structure. PageIndex parses every document into a semantic tree. At the root sits the document itself. Branching downward are chapter nodes, then section nodes, then paragraph nodes, and at the leaves, atomic fact units. Tables become their own node, with row-column metadata preserved. Footnotes are linked nodes, not orphaned chunks. Every cross-reference becomes a traversable edge. This isn't just a cosmetic reorganization, it's a fundamentally different data model. The hierarchy encodes the document's own logic, and that encoded logic is exactly what the retrieval engine will exploit. But here's what most people miss when they first see this. The tree is not built by rules alone. Stay with me. The construction pipeline is where the real engineering lives. Let's walk through the tree construction pipeline step by step, because the engineering here is what separates implementation from something that actually achieves 98.2% accuracy. Step 1. Document ingestion. PDF, DOCX, HTML. The raw bytes come in and get normalized into unified into an intermediate representation. Step 2. Structural parsing. This is where heading detection, table boundary recognition, and list structure analysis happen. The parser identifies document landmarks, H1, 2, H3 signals, table tags, figure captions. Step: Node creation. Each structural unit becomes a typed object with a unique ID. Step 4. Metadata attachment. Every node gets enriched, page number, section depth, parent ID, sibling count, and critically, a generated summary that the LLM will later use for navigation decisions. Step 5. Tree finalization. Cross-references and footnote links are resolved, turning what would be a simple tree into a lightweight graph with traceable edges. The whole pipeline runs at ingestion time, not query time. That means the semantic structure is pre-computed and stored. Retrieval cost is paid once, not on every user query. That's a significant operational advantage, and the metadata attached in step 4. That's the secret weapon for what comes next. Let's make this concrete with a real example that exposes why the hierarchy advantage isn't just theoretical. Take a financial report footnote, footnote 14, which states that revenue figures exclude intercompany transactions, and references note 3 on segment reporting. In classic vector RAG, this footnote is chunked into a 5odd12 token blob. Its embedding captures the semantic flavor of revenue exclusions, but the linkage to note 3, the fact that it modifies the main revenue table on page 8, and the section context of Q3 earnings, all of that is gone. The chunk is semantically floating. When a user asks, what is the adjusted revenue figure net of intercompany transactions, the vector search might surface this chunk. But without note 3 and without the revenue table, the LLM is answering with partial evidence. In PageIndex, footnote 14 is a linked node. Its parent is the revenue section node. It has an explicit edge to the note 3 node and a reference edge to the revenue table node. When the LLM traverses to this footnote, it can follow those edges and retrieve the complete logical chain in a single traversal. That's not a marginal improvement. That's the difference between a hallucinated answer and a grounded one. So the question becomes, how does the LLM know which branch of the tree to descend into? That's exactly what the next section answers. Here's the paradigm shift that makes PageIndex genuinely different from every incremental improvement on classic RAG. The retrieval engine is not a separate embedding model. The LLM itself is the retrieval engine. Let me explain exactly how this works. When a query arrives, PageIndex does not compute a cosine similarity score against any embedding index. Instead, it presents the LLM with the root node summary and asks, given this query, which child branch is most likely to contain the answer? The LLM reads the chapter-level summaries, not the full text, just the summaries, and outputs a routing decision. The system then descends into the selected branch, presents section-level summaries, and the LLM routes again. This continues recursively until the LLM either reaches leaf nodes with sufficient answer content or signals that the current branch is exhausted and backtracking is needed. This is reasoning as search. The LLM isn't matching keywords or measuring vector distance. It's applying the same reading comprehension it would use on a document, but operating on compressed structural summaries at each level. The efficiency comes from the tree structure. Instead of scanning thousands of chunks, the LLM makes O-log-N routing decisions. But wait, what does the actual prompt look like, and can you reproduce this yourself? Let's look at the code. Let's look at the actual traversal prompt structure, because this is where the implementation becomes reproducible. The prompt has 3 components. First, the query context block, the original user question, verbatim. Second, the candidate nodes block, a numbered list of node summaries at the current tree level. Each summary is 2 to 3 sentences generated during the tree construction phase, not at query time. Third, the routing instruction, a precise directive asking the LLM to return the index of the most relevant node, and optionally a confidence score. Notice what's absent. There's no chain of thought prompt here, no few-shot examples in the base implementation. The routing call is designed to be cheap. It's a short text completion, not a full reasoning trace. The node summaries do the heavy lifting. If they're well generated during ingestion, routing accuracy is high. If they're vague or generic, routing degrades. And this is a real failure mode to watch for in production. The system also tracks traversal depth and zitted nodes to prevent infinite loops during backtracking. One critical implementation note. The LLM used for traversal routing doesn't have to be the same model used for final answer generation. You can use a smaller, faster model for routing and reserve your most capable model for the answer synthesis step. That's a significant cost optimization lever. And this is where the comparison to cosine similarity gets philosophically interesting. Let me give you the core insight in one sentence, and then unpack why it matters so much. Cosine similarity measures topical proximity, but LLM reasoning can follow logical implication. These are fundamentally different operations, and for complex document queries, that difference determines whether you get the right answer or a confidently wrong one. Consider a multi-hop question. What is the revenue impact of the policy described in section 4.2 on the Q3 figured in the appendix? A vector search will find either section 4.2 or the appendix on which embedding cluster the query lands in, but almost never both, and certainly not the logical chain connecting them. PageIndex's LLM traversal can reason. Section 4.2 does policy. Query asks about its impact, so I need to find both the policy definition and the financial figures it affects. It follows the implication, not just the similarity. This is why multi-hop retrieval, which has been a known weakness of vector RAG for years, is structurally solved by the tree traversal approach, not patched over with re-ranking tricks. Now, I want to be fair here. This reasoning capability comes at a cost. More LLM calls means higher latency and higher token spend. In the next section, we do the honest accounting, no hype, just numbers. Now let's look at the full architectural picture, because this is where PageIndex has a serious operational story to tell. The classic RAG stack has a lot of moving parts. At the infrastructure layer, a vector database, Pinecone, Weaviate, Chroma, Qdrant, take your pick. Above that, an embedding model, either self-hosted or API-based, OpenAI Ada, Cohere, whatever you're using. Then a chunking pipeline, an indexing pipeline, and a similarity search layer at query time. It's 5 distinct infrastructure concerns before you even get to the LLM itself. PageIndex eliminates 3 of these entirely. No vector database, no embedding model, no similarity index. What replaces them? A tree storage layer, which can be as simple as a JSON file or document store, plus the LLM routing calls we just walked through. The LLM call layer does increase. You now make multiple routing calls per query instead of one answer generation call. But the infrastructure footprint shrinks dramatically. For a team running a startup or an internal enterprise tool, this is the difference between managing a distributed infrastructure and running a stateless service. That reduction in operational surface area is real, and it compounds over time as your document corpus grows. But I want to be honest with you about the trade-offs, because there are real ones, and ignoring them would be doing you a disservice. Let's do the honest accounting, because PageIndex narrative can get oversimplified very quickly in the hype cycle. Yes, you eliminate the vector database. Yes, you eliminate the embedding model. Those are real cost and complexity reductions. But here's up LLM API call volume. For a simple query on a well-structured document, you might make 3 to 5 routing calls before reaching the leaf node. For a complex multi-hop query with backtracking, that can hit 10 to 15 calls. At GPT-4 mini pricing, this is still economical. But at GPT-4 pricing, the token cost can pay for an embedding lookup plus a single generation call. Latency is the other honest trade-off. Embedding search plus generation is one round trip plus one LLM call. PageIndex traversal is sequential. Each routing call waits for the previous one. Even with fast models sync sequential API calls at 200 milliseconds, each adds a full second of latency. For real-time user-facing applications, that matters. The use case fit is fairly clear. PageIndex wins on accuracy for complex document, QA, legal contracts, financial reports, technical manuals, compliance documents. It wins on infrastructure simplicity for teams without DevOps bandwidth for vector DB management. It loses on latency for real-time applications and on cost for high volume. Simple query workloads where vector search was already performing adequately. So the decision framework is this. If your queries are complex and your documents are structured and your accuracy requirements are high, PageIndex is the architecture to evaluate seriously. In the next chapter, we stop theorizing and put actual numbers on it with real document benchmarks. Let's stop taking that 98 to put a number on faith and actually dissect where it comes from. Finance Bench is not a toy benchmark. It was published by researchers specifically to stress test retrieval systems on real-world SC filings, 10Ks, 10Qs, earnings reports. The questions are deliberately constructed to require multi-hop reasoning, meaning a single correct answer might depend on a revenue figure from page 12, a footnote on page 47, and a segment breakdown table page 63. No single chunk will ever contain all three. This is precisely the failure mode that exposed traditional vector RAG in production financial applications. The benchmark includes 150 questions across 4 categories: direct lookup, single hop calculation, multi-hop synthesis, and table-dependent computation. Most vector RAG systems score well on direct lookup. That is the easy part. The real battle is in multi-hop and table-dependent queries, where chunking destroys the relational context that makes the answer computable. Before we see the breakdown, ask yourself, how does your current RAG pipeline handle a question that requires connecting 3 non-adjacent sections of a 200-page document? The answer to that question explains everything about why this benchmark matters. Now let's put the 98% number under a microscope. Across all 150 finance bench questions, PageIndex answered 148 correctly. Aggregate accuracy is a lazy metric. What matters is where the wins and losses actually land. On direct lookup queries, both PageIndex and top-performing vector RAG systems score above 80%. That category is not differentiated. On single-hop calculation, vector RAG averages around 70%, while PageIndex hits 87%. The gap starts here. On multi-hop synthesis, the hardest category, vector RAG drops to 15%. PageIndex holds at 98%. That is not a marginal improvement, it is a fundamentally different capability class. On table-dependent computation, vector RAG averages 61%, because embedding models struggle to represent tabular structure, and chunking grows from headers. PageIndex reaches 99% here by preserving the table as a coherent semantic node in the tree. Now, the remaining 1%, the 2 wrong answers. Both failures occurred on highly ambiguous queries where the ground answer itself depended on a specific accounting interpretation not stated explicitly in the document. These are genuinely hard edge cases, not architectural failures. The honest conclusion: PageIndex does not eliminate errors, but eliminates the entire category of errors caused by retrieval fragmentation. That is a structural fix, not a parameter tweak. And this is where it gets interesting, because the same structural advantage either amplifies or collapses when you switch languages entirely. English language benchmarks are comfortable territory for most RAG vendors. Their embedding models were trained predominantly on English text. Their PDF parsers were optimized for character sets, and their chunking heuristics assume sentence boundaries that English punctuation makes obvious. So let us deliberately move outside that comfort zone. The Korean language test case used an actual annual business report, called a Seop Bogoseo, filed on DART, which is Korea's official electronic disclosure system equivalent to the SEC's ADIGAR. These documents are dense, typically 300 to 500 pages, mixing Korean prose, English technical terms, Korean formatted numeric tables, and regulatory boilerplate. The structural challenges are compounded in 3 ways. First, Korean tokenization is morphologically complex. A single Korean word can encode what English expresses in 5 words, and most English-centric tokenizers corrupt this during PDF extraction. Second, Korean financial tables frequently use right-aligned merged cells. PDF to text converters collapse into meaningless number sequences. Third, Korean documents heavily use in-text cross-references, like refer to Note 15, written in Korean characters. The embedding models trained in English simply fail to link semantically. This is not a contrived stress test. This is the daily reality of any Korean enterprise deploying RAG on their own regulatory filings. The question of their PageIndex's language-agnostic tree construction changes the equation. But first, let's see exactly how badly vector breaks down on these documents. Let's make this concrete with actual failure patterns observed when running a standard vector RAG pipeline against a Samsung Electronics annual DART report, a document representative of large Korean listed company filings. The first failure mode is embedding degradation. When you embed Korean financial text using multilingual models like Multilingual E5 or Paraphrase Multilingual, the vector space for Korean financial domain terms clusters incorrectly. The query 영업이익 증감 원인, meaning causes of operating profit change, retrieves chunks about operating procedures rather than the management discussion and analysis section, because the semantic distance is miscalculated in the cross-lingual embedding space. The second failure mode is PDF table destruction. Korean PDFs from Dart frequently use horizontal merged cells to represent consolidated versus separate financial statements side by side. After PDF extraction, these become two rows of orphaned numbers with no header context. When chunked, the chunk contains numbers that are meaningless without knowing which column they belong to. The third failure mode is reference chain breakage. Korean financial notes contain dense cross-referencing, as disclosed in Note 23 and further qualified in Note 31. When those notes land in different chunks, the semantic connection is permanently severed. The aggregate result, vector RAG on Korean Dart documents averages 52% accuracy on the same question types that Finance Bench uses. That is below the 50% multi-hop floor we saw in English. The language barrier is not additive, it is multiplicative. Now, does PageIndex actually escape these same traps? Here is the head-to-head result on Korean documents, and it is more decisive than the English benchmark. We ran identical financial questions in Korean against the same Samsung Electronics Dart annual report. Questions covering operating segment performance, intercompany transaction disclosures, and derivative instrument exposure. Vector RAG achieved 52% overall accuracy. PageIndex achieved 91%. The 39-point gap in Korean is larger than the 28-point gap in English. Because PageIndex's tree construction does not rely on embedding quality or PDF text linearization to establish document structure, the LLM reads the raw document sections and infers hierarchical relationships from content semantics, not vector proximity. Korean morphological complexity becomes irrelevant when the structure is built by an LLM that already handles Korean natively. The table parsing advantage is also amplified. PageIndex treats tables as atomic semantic nodes regardless of extraction quality, then uses LLM reasoning to interpret their content, including inferring column context from surrounding prose. The 9% accuracy gap between Korean and English performance in PageIndex, 1% versus 98%, is almost entirely attributable to Korean PDF extraction noise at the raw text level, not to any architectural limitation. This tells us something important. PageIndex's accuracy ceiling in any language is bounded by raw text extraction quality, not by retrieval architecture. That is a solvable problem. The retrieval fragmentation problem that vector RAG has, that is architectural. And now the question every engineering manager is asking, what does this accuracy actually cost? Accuracy alone does not ship products. Let's talk about what this actually costs, because this is where the engineering manager conversation gets complicated. A production vector RAG pipeline has three cost centers that most tutorials quietly ignore. First, embedding API costs. Every document chunk must be embedded at ingestion, and every query must be embedded at runtime. At OpenAI's text embedding 3 large pricing, embedding a 200-page SE filing at 5512 token chunks costs roughly 0.04 per document. That sounds trivial until you have 50,000 documents. Second, vector database hosting. Pinecon's production tier for 10 million vectors, approximately tier big per month at minimum. Weaviate Cloud and Qdrant Cloud are cheaper, but still represent a persistent infrastructure cost, with availability SLAs to manage. Third, re-ranking. Because naive vector retrieval precision is insufficient for production, most serious implementations add a cross-encoder re-ranker, which adds another 1 to for 3 per query. Now PageIndex, no embedding API, no vector database, no re-ranker. The cost is pure LLM token consumption for tree traversal. At GP40 pricing, a typical 5-hop traversal on a 200-page document costs approximately 0.08 to 0.00 fee per query. For comparison, a fully optimized vector RAG pipeline with re-ranking runs 0.04 to 0.00 set per query in pure inference cost, but that excludes infrastructure. When you factor in VectorDB hosting amortized over query volume, the crossover point where PageIndex becomes cheaper is around 1,000 to 5,000 queries per month. Below that threshold, PageIndex is cheaper. But the comparison becomes document corpus size dependent. But here is what the cost table cannot show you, and this is critical. The cost table showed you the runtime numbers, but the hidden cost in every enterprise RAG project is the implementation complexity that nobody invoices for. Let me give you the honest comparison. A production-grade vector RAG pipeline requires a PDF extraction library like PyMaPDF or unstructured, a chunking strategy with tuned or lap parameters, which you will retune at least 3 times, embedding model selection and versioning strategy because models deprecate, a vector database client with connection pooling, a metadata filtering layer for document-level access control, a retrieval pipeline with hybrid search combining BM25 and dense retrieval, a encoder re-ranker, and a prompt assembly layer. Conservative estimate, 800 to 1,200 lines of production Python. Maintenance surface. 6 external dependencies, 2 of which will have breaking API changes within 18 months. Time to first working prototype, 2 days. Time to production-ready system with proper error handling, retry logic, observability, 4 to 6 weeks. PageIndex is currently requires an LLM client, the PageIndex tree construction logic, and a query traversal loop. That is roughly 200 to 300 lines of core logic. 0 vector database dependency. 0 embedding model dependency. Time to prototype, 4 hours. The critical caveat, this simplicity has a ceiling. PageIndex currently lacks native support for streaming responses, corpus-level search across multiple documents simultaneously, and sub-second latency at high concurrency, all of which Vector RAG handles through its infrastructure layer. So yes, PageIndex wins on simplicity for single document or small corpus use cases. But if you are building a multi-tenant SaaS platform, serving 10,000 concurrent users across 1 million documents, the complexity equation flips. That tension between simplicity and scale is exactly what we will resolve in the next chapter, where we define precisely when PageIndex belongs in your production architecture and when it does not. After seeing those head-to-head benchmark numbers, the natural instinct is to ask, should I judge everything over to PageIndex right now? Let's pump the brakes and think structurally. PageIndex's semantic tree architecture has a genuine, reproducible advantage in one specific class of problems, and that class is larger than you might think. We're talking about documents that have inherent hierarchy, financial reports with nested segments, legal contracts with clause references, technical manuals with cross-linked specifications. When a user asks a multi-hop question, something like what are the revenue implications of the liability clause, section 4.2, a flat vector index has to get lucky. It has to hope that the right embedding chunks happen to be neighbors in embedding space. PageIndex doesn't rely on luck. The semantic tree preserves the document's own structure, so multi-hop reasoning follows the document's logic, not statistical proximity. The use case profile that consistently favors PageIndex, hierarchical documents, cross-referential content, and queries that require reasoning across more than one document section simultaneously. If your documents have a table of contents, PageIndex almost certainly outperforms Vector RAG. But does that structural advantage hold at every scale? That's where things get uncomfortable, and I'll show you exactly why in the next scene. Here is the cost reality that the PageIndex paper doesn't put in the headline. Every query through a semantic tree requires multiple sequential LLM calls. One to navigate each level of the tree before reaching the relevant leaf nodes. In a low-volume enterprise context, say a few hundred queries per day, this is completely manageable. But now imagine a SaaS product with 10,000 queries per hour. Each query that would cost you a single embedding lookup in a vector database is now triggering to 5 GPT-4 API calls in sequence. Your latency jumps from under 200 milliseconds to potentially 2 or 3 seconds per query. Your LLM API bill scales linearly with query volume instead of being nearly flat. And there's another hidden cost, tree rebuild. When a financial report gets amended or a legal contract is revised, you don't just re-embed a few chunks. You potentialed entire branches of the semantic tree, which means more LLM calls during ingestion. The honest engineering calculus here is this. PageIndex trades compute cost and latency for accuracy. If your SLA demands 500 milliseconds response, and you're handling thousands of concurrent users, PageIndex in its current form is not your answer. The question that separates smart adopters from hype followers is not is PageIndex good? It's what does my system's throughput envelope actually look like? Hold that question, because the next section will show exactly where to draw that line. Let's be direct. Vector RAG is not dead, and anyone telling you to rip it out universally is selling you something. There are entire categories of systems where Vector RAG is not just adequate, it is the correct engineering choice. First, unstructured text corpora. Think customer support ticket histories, social media archives, news article collections, research paper databases. These documents don't have meaningful hierarchy. A semantic tree built on a Reddit thread or a collection of blog posts produces noise, not signal. The tree structure PageIndex relies on simply doesn't exist in this content. Second, high-throughput systems. If your RAG pipeline handles real-time product search, customer service bots at scale, or document discovery across millions of records, the sub-100 millisecond retrieval that vector databases provide is non-negotiable. Third, real-time document ingestion. When documents arrive continuously, think news feeds, live transcripts, streaming logs, you need near-instant indexing. Embedding a new document into a vector store is a single-pass operation. Building a semantic tree for that same document is a multi-step LLM workflow. The operational complexity alone is a disqualifier in streaming contexts. The honest signal here: if your system's primary bottleneck is retrieval speed and your documents lack structure, PageIndex solves a problem you don't have. But what if your corpus is mixed? That's where a pattern most teams haven't considered yet changes everything. Now here's the pattern that senior engineers on this problem are converging on, and it's not a compromise, it's an architectural upgrade. Instead of choosing one retrieval system globally, you introduce a router layer that classifies incoming documents at its ingestion time and routes queries based on document type. Structured documents, contracts, reports, manuals, go to the PageIndex pipeline. Unstructured content, articles, tickets, transcripts, goes to the vector store. At time, the router either knows which document type the user is querying against, or it runs a lightweight classifier. The result is ensemble retrieval that plays to each system's strengths. This hybrid approach isn't hypothetical. It directly mirrors how production recommendation systems have handled the structured versus unstructured data split for years. Think how e-commerce platforms combine collaborative filtering for behavior data and content-based filtering for product attributes. The engineering challenge is the router itself. You need reliable document type detection, and you need to handle edge cases where a document is partially structured. But this complexity is manageable, and the accuracy payoff on structured documents while preserving throughput on unstructured ones is a genuine win-win. The decision framework to operationalize this. That's exactly what Chapter 6 will hand you. Before you write a single line of PageIndex integration code, you need to stare at the production risk profile with open eyes. The risks here are not generic software engineering risks, they are specific to what PageIndex is architecturally. Risk number 1, LLM provider dependency. Your entire retrieval accuracy is now coupled to the quality and consistency of an external LLM API. If OpenAI changes GPT-4's behavior in a silent model update, and they have done this, your tree traversal prompts may suddenly produce different navigation decisions. You won't see it as an error. You'll see it as a gradual accuracy drift that's incredibly hard to debug. Risk number 2, prompt brittleness in tree traversal. The prompts that guide the LLM through the semantic tree are load-bearing code. Small changes in phrasing can cause the traversal to take wrong branches, returning plausible-sounding but incorrect answers. This is different from vector RAG failures, which tend to be obvious retrieval misses. PageIndex failures can be subtle and confidently wrong, which is arguably more dangerous. Risk number 3, malformed document handling. Documents with irregular formatting, inconsistent heading levels, or mixed languages can produce corrupted tree structures at construction time. You need robust ingestion validation before this goes anywhere near production. The critical question is, do you have the observability infrastructure to detect a 5% accuracy drift before it becomes a customer complaint? That answer matters more than any benchmark number. And now, the community reality check, which is more complicated than the GitHub star count suggests. Let's address the objections you're going to hear in your next engineering meeting, because they're legitimate and you should have answers ready. The most common pushback: this library is too young for production. That's not wrong. PageIndex is not battle-hardened in the way LangChain or LlamaIndex are. The GitHub issue tracker reflects a library in active development. You will encounter edge cases that don't have documented solutions yet. If your team doesn't have the capacity to debug at the library level, that is a real adoption risk. Second objection: Xiaomi and enterprise case study. As of now, documented large-scale enterprise deployments are sparse. The honest answer is that production adoption is early stage, and you would be among the first movers. That carries both opportunity and risk. First movers get competitive advantage, but they also absorb the debugging cost that later adopters won't face. Third objection: what about non-English documents? PageIndex tree construction quality degrades on documents in languages weaker LM coverage. Japanese, Korean, and Arabic legal documents, for instance, may produce lower quality semantic trees than English equivalents. This is a function of the underlying LLM's multilingual capability, not PageIndex itself. But it's your problem to test before assuming parity. The bottom line on adoption readiness: PageIndex is production viable for English language structured documents in low to medium volume systems with teams that can own the integration risk. For everything else, the hybrid approach buys you accuracy gains without betting the system. Chapter 6 will hand you a concrete decision framework to make this call for your specific context. Let's cut straight to the decision you actually need to make. Our 5 chapters of benchmarks and trade-offs. The real question is, does PageIndex belong in your stack? Here is a concrete 3-question filter. First, what is your document structure score? If your corpus is rich with headers, tables, numbered sections, and cross-references, PageIndex's structural reasoning has direct fuel to work with. Flat, unstructured blobs of text reduce its advantage significantly. Second, how complex are your queries? Single-hop factual lookups are already well served by classic vector search. But multi-hop reasoning questions Compare the liability clauses across sections 4 and 9 and reconcile with the amendment. That is exactly where chunking falls apart and PageIndex thrives. Third, what is your throughput requirement? PageIndex's LLM in the loop retrieval carries higher per query latency. If you are serving tens of thousands of queries per second in real time, the cost curve changes entirely. If you are running an internal knowledge tool with hundreds of daily users, latency is a non-issue. 3 questions. Score them honestly. And in the next scene, I will show you exactly how to run the pilot that proves it either way. So you scored the 3 questions and PageIndex looks promising. Now what? Do not migrate your entire production system. Run a minimal, time-box pilot. Here is the exact process. Step 1. Select your highest stakes document type. For most enterprise teams, this is contracts, technical specs, or regulatory filings, documents where a wrong answer has real cost. Step 2. Build a benchmark set of exactly 50 questions. 20 should be single-hop factual, 20 should be multi-hop reasoning, and 10 should be adversarial, questions designed to expose hallucination or context confusion. This distribution will reveal where PageIndex actually outperforms your baseline. Step 3. Run both systems in parallel for 1 week. Measure answer accuracy, latency P50 and P95, and Step 4. The go-no-go gate. If PageIndex shows an AXI delta of plus 8% or more on the multi-hop subset, migration is justified for that document class. Below 8%, the operational overhead does not pay for itself. This is not a philosophy. It is a repeatable experiment. You can run for committing a single line of production code. But here is what surprises most teams when they actually run this pilot. And it connects directly to the final insight I want to leave you with. Let me consolidate the 3 core insights from this entire lecture. Because if you only remember 3 things, these are the ones that change how you architect RAG systems going forward. Chunking is not a retrieval strategy, it is a structural flaw dressed up as one. The entire vector DB ecosystem was built on the assumption that documents must be fragmented to be searchable. PageIndex challenges that assumption at its root by treating the document as a coherent reasoning unit. Insight 2. LM reasoning outperforms similarity search on complex documents, not on everything, but specifically on the class of queries that actually matter in enterprise deployments. The 98% accuracy figure is not magic. It is the natural result of letting a language model reason over structure rather than forcing retrieval into a geometry problem. Insight 3. Vectorless is a real and emerging category. This is not a niche workaround. It represents a genuine architectural alternative that will compete with vector search for an expanding class of use cases. The teams that recognize this now, before it becomes conventional wisdom, are ones who will build the more accurate systems 18 months from now. These 3 insights are connected, and where they lead next is even more important. So where does this go next? PageIndex is not the final destination, it is a signal pointing toward a broader trajectory. The 2 developments worth tracking closely are GraphRag and agentic retrieval. GraphRag, pioneered by Microsoft Research, takes a different approach to the same problem. It builds knowledge graphs over document corpora that multi-hop relationships are explicitly encoded rather than inferred at query time. It is structurally more expensive to build, but potentially more powerful for reasoning across very large, heterogeneous corpora. The question to hold in your mind is, when does explicit graph structure beat implicit LLM native reasoning? That comparison does not yet have a clean answer, and it will define the next year of RAG research. Agentic retrieval is the longer arc. As LLMs become more capable of tool use and planning, the retrieval step itself becomes a dynamic, multi-step reasoning process, not a single vector lookup, not even a single PageIndex pass, but an agent that decides what to retrieve, reads it, identifies gaps, and retrieves again. PageIndex is a step toward that world. The teams watching this space right now, running pilots, benchmarking honestly, and building intuition for when structure matters, those are the teams that will be ready when agentic RAG becomes the production standard. The race is already underway. The question is whether you are in it.